Hello? Good? Yeah?
Yes, can you hear it?
Hello? Hello?
So it's a pleasure to introduce Werner Kappen to this day. So Professor Kappen got his PhD in Rockefeller University in New York, and then was working at the Philips lab in Germany. Am I correct?
Yeah.
And,
Netherlands.
1997, he obtained a position at the Radboud University in Mannheim. And he has actually a good experience, not only at the university. I will visit the university someday, so I will learn well how to study. And the microphone. Okay, so then he has actually been not only working at the university, but he was also telling us during lunch about 3 companies or different companies, saying which he was actually funding related to different applications of machine learning, statistical physics, inference methods in very different fields. He was mentioning things going from health system to forensic projects related, for instance. He was mentioning also part of the collaboration with the Spain government for this initiative related to the Ley de Memoria Histórica for identify bodies of the Civil War. And he has been working in very different fields, actually, in statistical physics, in inference theory, and in biological system, neuromorphic approaches. More recently started to work in quantum, and I like the definition that he gave to me today, that he is a science tourist, in the sense that he likes to work in different topics and in different subjects. So it is a pleasure to have you here. He will be here around also the beginning of the next week. So tomorrow, the day after, and the beginning of the next week, if someone is interested to have a chat with him, just please tell me so I can, or directly him, but just to prepare an agenda. Okay? Please ask.
Thank you, Roberta, for this kind invitation. Thank you for inviting me here. I'm very happy to be here. I have to set up this keyboard thing. I'm not sure. Ask is. And now? Okay, and it should work. No, this is not. Is this on? This is off, maybe. And now it works. Okay, yeah. So thank you for having me here. I'll be here for a week. Let me introduce myself a little bit. I'm an old guy. It's been in science for a long time. I got my PhD in '87 in high energy particle physics. Then I was working in combinatoric optimization for a few years. Then I started in Nijmegen in a neuroscience department working on neural networks, and got into stochastic neural networks. That did a lot of approximate inference, taught myself the statistical physics, did things like belief propagation, Monte Carlo methods, variational methods for message passing in such complex systems. Then around 2004, I moved into the area of stochastic optimal control theory. So a leitmotif here is that I always look for, I'm interested in computing for intelligent systems. I'm always looking for efficiency in computation. So in the 90s, that was about graphical models, about probability distributions. With the control theory is also a very hard computational problem. So I try to address that. And that's the topic of today's talk also. So I will present this work. And then around 2017, I moved into the area of quantum, also with the same objective, that I wanted to see whether quantum computer could help speed up computation for machine learning kind of applications. In particular, as an example, say you want to sample from a distribution, can you prepare such a distribution as a quantum state, and can you just get measurements of that quantum state as a way of sampling, right? Okay, so this is that. So I'm working on that. I'm not presenting on this because this work is still very much in progress. I have various papers on this. If you're interested in, we can talk about that. In the meantime, I also did some work on neuromorphic computing. In a collaboration, we built maybe the world's smallest neural network. One neuron, one atom. So we have on a substrate with a STM setup, we can build a little neural network. And I'm also not talking about that. So that's more or less my research. And then I have some applications. So I've been very much interested in medical diagnosis, been working on that off and on, building a system that helps doctors to give a rationalized decision on what kind of diagnosis the patient has. We have been working on, there's a company on missing person identification, this Bonaparte system. Roberto already mentioned it. So if there's a plane crash, there is people dead, and there is families who miss people, and so these have to be matched. So it's a bipartite kind of a matching structure, and you're matching a body part against relatives of that body part. So it is an indirect kind of matching. We do this for Interpol, for instance, the Interpol, all their international searches, they use our software for this. And we now also are this project in Spain with which is about 15 labs all over Spain that are now working with our system. And then I also have hobbies. I look at quantum models for neuroscience, because I'm sort of done with the standard neuroscience, and I want to see whether we can do something more exotic with that. I'm also very much interested in consciousness research. I got that interest over the last few years, and I'm investigating the impossibility or possibility of mathematical theory of consciousness. I stress these are hobbies in the sense that I take an active interest, that I read those kind of research, but I have not really contributed to that field in any scientific sense myself, and I play the piano. So now you know everything about me. Okay, so we're going to talk about optimal control theory. And what is it? So given a certain state and a future desired state, what is the best, cheapest, fastest way to get there? So for instance, this giant wants to kill this little man. And so this is the current state. And so he has to swing this tree. And he can do that in various different ways. And there's an energy associated with that. So that's an integral over time of some cost. You can do it in a more or less optimal way. And then there is an end cost that is maybe is quantifying whether he actually hit the little guy or whether he misses the mark, something like that. So these are typically, this is the control setup. So control occurs in many applications. So, for instance, I mean, we ourselves are controllers, which are learning controllers, where we love to play with blocks as kids to learn about the physics of the world and to learn about our own body and how to control that. Multi-agent systems, like this dog is trying to control a herd of sheep, and the sheep are all going all over the place, and maybe there are multiple dogs. Inverse problems that you have, like this flock of sparrows that or sterling, well, sparrows or sterling, I don't know. There are birds that fly over Rome. By the way, this is Cavagna's work, and you may want to use a control way to understand what's happening. So to see whether you can do sort of an inverse engineering of this observed system, you have some observed behavior and say, okay, these birds are optimizing this kind of a way, and you can maybe formulate it as a control formulation. And that also all holds for things like population genetics that you see in genetics, some dynamics, and you may get a control idea of it, immune system, predator prey kind of things, how to treat, how to optimize treatment schedules for drugs, financial portfolio, and maybe possibly quantum devices, which is something that I'm start to look at now, and I have no ideas of whether that could work, but that's in my interest. So these are control problems, but why would you be interested in stochastic control problems? And the example I always give is this particular scenario. So imagine this little spider that wants to go home. And so he can either go over this little bridge, or he can walk around the lake. Now the lake is a very big detour. So if nothing else happens, then the optimal path that he plans is to go over the bridge, and then he gets home. But now suppose that the spider just comes out of the bar, has been drinking a few beers, and is slightly uncertain about his coordination. And as you may have experienced yourself in that situation, if you give a command to go left, there's a 10% chance that you actually go off to the right. So there's noise in the problem now that is not under your control. And so then if he goes over the bridge, there may be a small chance that he actually falls off the bridge, and that makes the cost of this path, the expected cost of this path, very high. And so now maybe the cheapest route is actually to walk safely around the lake. So the morale of the story is that you add a little noise to this problem, and you get not a little bit of different solution, but you get a qualitative change in the solution. And the analogy with physics of a phase transition is very accurate. So you get actually a phase transition, that you go from a low temperature kind of control solution to a high temperature control solution. So these are qualitatively different and therefore are worth of studying. So, so the optimality depends on the uncertainty. So the outline of the talk is I will going to tell you a little bit about stochastic optimal control theory, and particularly about this development that I did myself some time back. And then it turns out that actually there's a tight relation between what this theory says is that the optimal control can be computed by sampling. And so then the rest of the talk is about how to sample. So you can sample in different ways, and there is something called importance sampling, and I will explain to you about that. And I will explain the relation between the importance sampling and the optimal control. And then I will present for you a method how to actually get to a good sampler and actually also get to a good controller in an iterative way. And that will be, and then there will be some examples along the way that will hope to guide your intuition a bit about this talk. Okay, so first the stochastic control theory. So suppose that I have this one-dimensional system. This is state, this is time, and I have two end positions, and I want to reach one of those. So I start here at the origin, and I have some dynamics, and I want to go to either one of these two goals. So this is to set the notation. Also, I have some stochastic differential equations setting the dynamics, and I have some noise here, and I have here a state. And I have a function of the state, and I have here a control, which we have to determine. So, so the given, suppose that the control problem, suppose that at time t, you are in state x. You want to find the control, which is this thing, which is the control function for all the remaining time and for all states. This is a feedback controller. This function, you want to find this function that minimizes this cost. And the cost is depends, of course, on the control and depends on where you are and at the time. And it's an expectation value of everything that can happen in the future. So you'll say at time 1, you're at a particular state, and where do you move? You go there, or you go there, whatever. And so it's an expectation value consisting of these two parts that I mentioned before. There is a path part, a trajectory part, and there's an end part. X capital T is the end time here. And so this is in general the setting that you want to optimize. So, so the standard way to solve this is what is called Bellman equation, and the Bellman equation has this notion which is called optimal cost to go function. This is J. So suppose we are at some intermediate time t and at some particular state, and we have to solve the control problem from that point. And suppose that we do that, we have solved it, and we call the result. We call it J. It's a function of x and t. And it's called the cost to go. It's the least cost you have to pay from that state at that time to come to the end time. That's the cost you have to pay, right? So suppose I want to go from here to there, and I'm now already here, and then I still have to go to there. So the shortest path will be the cost there. It's all the possible wiggly paths, but the shortest path will give me the cost. Now this J satisfies the partial differential equation, which is known as the Bellman equation, and I'll give it here in this particular case. So there is this cost, which was in the integral on the previous slide. This is the dynamics, and this is a drift term and a diffusion term. And so this is a partial differential equation that you need to solve with end conditions. So because if you are at the end time, you know that the optimal cost is just your end cost. And then and the optimal control that you find is basically at each time, at each state, you do the minimization. So it is the argmin of whatever you have here. This is the optimal control. Okay, so this problem is solved backward in time, and that is because the solution at the earlier times, they depend on the solution at later time, right? Not the vice versa. So if I want to solve from here to there, so in 2 steps, then the solution that I take here depends on the solution that I have there, right? Because on the optimality of that. But the solution that I have here does not depend on what I did in the past, because I'm already here. It's conditional where I am now. So I can forget all about the past, right? So that's why you get this backward solution. Okay, so that's very, very short about control theory in terms of the Bellman equation. So if you have any questions, by the way, please interrupt me, so then you can also slow me down, because I have a tendency to speak fast, and then it's a good way. This one? Well, it's actually not linear, because if you minimize over u, you get something gradient u, and it actually becomes horribly nonlinear. So the min over u is sort of making it suggest that it's linear, but it's not, right? So for instance, if this function would be u squared, right? If you minimize, then you get u is equal, and this one is, for instance, this one is linear in u, yeah? Then you would u squared plus u gradient. If you then minimize with respect to u, you get that u is equal to gradient j, and you would put it in, and you get gradient j squared. So it's actually not linear in, it's not linear. Yes, yeah, and this minimization is, of course, very nasty, yeah. So this is a general, so there's much to say about that, but let's not go into details. Okay, so this is the setting that you need to do. If you do that for this particular problem that I started with the starting at the origin and going to one of these 2 slits, you get this optimal cost to go looks like this. So it is, this is time, this is space, and this is j. So red is high, blue is low, yellow is intermediate. So you see that if you are here somewhere, you have to, so basically the way to think of this cost to go is that the control is roughly the gradient in j. So at this point, you see that it's bimodal. So you either have to steer here or you have to steer there. At an earlier time, it is unimodal. It just goes from high to low to high. And you have to basically steer towards the middle, right? So it's also, this j is also known as the anticipated potential. It's the potential that that has a boundary condition at the end time, and you move it by the differential equation to an earlier time, and it tells you how to act now on something that you optimize in the future. Right? So that's the anticipated potential. So here you see this is quite curious. So it says basically that if you start the origin, you basically should do nothing. You should stay at here, basically stay here. And then at some point, you could not keep on doing that, but at some point you have to actually steer one to this one or that one, right? And of course, there's noise that's taking you all over the place. So here you see trajectories that are computed under optimal control. They don't look very optimal, and the reason is that you don't control the noise. So the noise is whatever it is, so it will do its thing, and so these are the control trajectories. So this is distribution trajectories under optimal control.
Excuse me.
Yeah.
In
this case, oh, sorry, yeah, I did not specify it. So in this case, I have the cost function is just the end cost, which is low cost for the 2 red dots and high everywhere else. And this term is just quadratic in U. Sorry, just quadratic cost on the control. Yeah, so yes, yeah. Thank you for that question. So in that case, and the dynamics is just U. It's just linear. So this f is just u in this particular example. Okay, so you get this solution, and keep in mind that it defines the distribution over trajectories, right? This procedure in the end. Okay, so now, yeah.
That example, I'm confused by the time boundaries. So in your initiation problem is fixed on the final time t capital T, but the process is also, so you give an initial condition for the process, and then the initiation is.
So okay, okay, yeah. So here it is. So your initial, at each time you are at some state x, which is this, right? And then you have to solve the control trajectory from there to the end. And the control trajectory is not a trajectory, it's a control function because it's a state feedback controller. Yeah. And that you do it every time. And that problem has a boundary condition at the end time where this J reduces to this end cost only. There's nothing else to optimize. You just have the end cost. Yeah. Okay. Yeah, more questions? Because this is the basics of the control theory. No. Okay, so now we go to this idea of the path integral control. So here we make a particular assumption about the dynamics. So we say the dynamics, that was this F, is now of a state-dependent function and another state-dependent function times the control. But this state-dependent function that multiplies the control is the same as the state-dependent function that multiplies the noise. Okay, so this is the particular setting that we have now. So you can think of, if you put the control equal to 0, you could say, well, this is an arbitrary complex dynamical system. These functions can also be explicitly time-dependent if you want to. But the control acts in a particular way on these arbitrary complex systems. Basically, it acts in this linear way, but multiplying some state-dependent function. And the control cost that we had, that also splits into in a state-dependent part and a quadratic term. Okay, so these are the particulars of this path integral control. So this is a linear in multiplying the state-dependent function, and here quadratic control. So this is that cost that we get now. And we can write this as an expectation value of this dynamics, where we specifically say that we do this dynamics with a particular control U of this function S, where S is just this whole thing, and we add this thing which has expectation value 0, but we'll need it for later for the definitions. Okay, so this is the rewriting for this particular dynamical system. And so these are the control functions. So this is the control function. So this U stands for this whole path of controls here. And this also is the whole path of controls. And this thing depends on the trajectory, right? So this is give you a trajectory over time, which is this tau, and it gives you a value of this S. And the EU is a sampling with control of this particular control function. Okay. Okay, so this is this setting. Now in this case, if we now redefine this psi in this way, that the cost to go is now a log transform of this psi, then the Bellman equation that we had, this equation, if you do that in here, you can do the minimization exactly, and you get a nonlinear equation, and you do the log transform, and you end up with a linear equation. And the result is this. So you get this kind of imaginary time Schrödinger equation kind of structure. And so the DDT comes from the DDT. So this is this thing. You see the gradient term, the diffusion term. So all the terms are there. Because of the log transform, you get that the end condition is now given as this. And lambda is a scalar number which takes the role of a temperature, and it is basically the product of R times nu. So here should be an identity matrix. So this is a further condition, is that the matrix R that appears here, but this is one-dimensional case, but you usually get U dagger RU. So there's a matrix here. This matrix, if you multiply it by this matrix, the noise covariance matrix of the system, that the product of these two matrices has to be proportional to the identity matrix, and the proportionality is this lambda, and it is the temperature of the system. It sort of says that that in so if you say r times nu is lambda, then so if you take this lambda to be a constant, then you say that if the situation is equivalent if when the noise is large and basically it says that directions that are very noisy are also very controllable. You have large control on that, and the directions that have very small noise are you cannot put control, because basically the control cost is r will go to infinite for those directions. So there's a proportionality. So it also puts down this statement that the directions this relation that I said before, that the control acts through the noise direction, it has to hold for all dimensions that are in the system. So you cannot, for instance, have that you have a two-dimensional system in which both have noise and only one has a control, right? Because then this doesn't match, because then there has to be a match between the control and the noise. Okay, so this is this system, and we get this kind of equation. And now, so this you may know, so from your quantum physics, you may know that this equation has a solution as a path integral. So this psi can be solved as a path integral, and it is basically given as the expectation under u of these trajectories of e to the minus s, where this s was defined on the previous slide. So this is a closed form solution as a path integral. And the control becomes basically this expression, where you get the expectation of the infinitesimal noise weighted by this s and normalized in the limit of time increments going to 0. And this is the sampling control. So this is the control that you use here. So there's a lot happening here. So I'm telling you, I have this system, this dynamics, I have this cost. I want to compute the optimal control, yeah? And the optimal control, I give you formulas, and the formulas involve sampling, and the sampling involves a control, and that control is arbitrary. So I can sample with control 0, I can sample with another control, and all these formulas, they all are formulas for the optimal control. So here, this expression on the left-hand side is the optimal cost to go, or related to it through this, and it does not depend on the particular control that you use. It's optimal, but you can estimate it with different controls. If I change the u, whatever u I take, I always get the same quantity. And here the same, the optimal control depends on the control that I sample plus this, but this right-hand side in total does not depend on u. It drops out. But of course you can imagine that if I have so suppose that I have a sampling problem. I start here at the origin. I want to go here, and my native dynamics is dx is u dt plus dw. So if I sample with control 0, I get trajectories that go like this, and it will be hard to reach the goal. I can also sample with other dynamics, which will be much better, and I get much better to the goal. So it's about the efficiency of the sampling, but the asymptotic formula are correct for all use. Okay. So this is the idea, the essence of the idea of the path integral. So here's another way of viewing it. So suppose that I have this dynamical system, and this determines a distribution over trajectories which are indexed by u, which is a particular control function that I use. So this is one distribution. And let's say that we also have another one where we put the control equal to 0, and we call this P0, this one. And so these are distributions over trajectories, and I can look at the distance between these two distributions. And this is measured by the Kullback-Leibler divergence between these distributions. So this is the expression for it. And if I compute it for these kind of things, what comes out is 1/nu times the quadratic control cost here. So that means that the cost that we had sorry, there's an expectation missing here. Expectation over U is missing here. That's coming from here. That means that the quadratic control cost that we have here, we can identify as a KL divergence in that sense. So this term, expectation, is equal to this term. And the other terms, this one, is actually the S that we had defined before with control 0. So this cost, which depends on the control, we can now write as a cost that depends on the distribution over the trajectories, right? So here we'll have a cost as a function of controls. Here we have a cost that is a function of a distribution. So we can write it in this way, right? It's a distribution. And now this thing, you see that if you're familiar with that, if you minimize this thing with respect to PU, you will easily find that the optimal one is just given by P0 e to the minus s over lambda by optimizing this thing. If you optimize this with respect to PU, so you find that the P star is this one. And so the psi is actually the integral over this thing, which is exactly equal to the normalization constant that we defined before. So if we fill this into the cost, we find that the optimal cost is minus lambda log psi, which is again the expression that we had before, which is the same as this expression here, minus lambda log psi here. So what we find is that here we have another expression for the distribution over trajectories under optimal control. So here, previously we had this expression here, here. So we had a distribution over trajectories given by the optimal control. We had computed the optimal control, and we had this distribution over trajectories. Now here we have another one, which is also optimal. It's the same, and it is the zero control, and it is weighted by that, and is this. So we have two distributions, and we can visualize them. So here's the one that we just had. Here's the new one. So here we sample according to the to P0, which is the uncontrolled dynamics. We get some trajectories like here on this picture, and we weight each line we color it with e to the minus s, with the cost of that trajectory. And the ones that get close to the goal, they become black, and the ones that stay finally off the goal, they become white. And here was the previous one where we had explicitly computed the control and simulated trajectories over that. And the statement is that these two trajectories, these two distributions are identical. And they are related by a shift of measure, which relates to what's called the Girzanov theorem. So in fact, here I had control 0, here I had the optimal control, but in fact, there's a whole slew of distributions which are all identical where I compute any control here. So all these distributions are in fact the same. So if I put U as 0, I get this one. If I put U as optimal, I get that one. But anywhere in between, I can also do that. So there's all these distributions, right? So we have this relation. So any questions about that? Yeah.
Is this an approximation or is it exact?
This is exact. This is exact.
No 740.
No. This is exact. Yeah. Of course, this U has to be optimal.
Yeah.
And the time discretization has to go to 0. And there are some regularity conditions, but besides that, it's optimal. It's exact. Yeah. So the control problem is defined as optimizing an expectation, right? So it's expected value. So think of a Gaussian. So you want the mean of that Gaussian to be somewhere as low as possible. You don't care about the variance of the Gaussian. Oh, definitely. So we'll come to that. Definitely. So we're going to come to that. Yeah, that's exactly the way. So, okay. So let me just give you an example. So here we have again this simple system with U is this. This is the one that I defined, not defined before. This is a quadratic control cost, just end cost on the state. We want to reach these two, either one of these two states. This is the dynamics that we have. We want to find U. You can actually do it analytically to solve it in this way, but you can also do it by sampling. You get these kind of samples. And what you find at the different times is basically this picture that we had here before, this picture here. At different time slices, you see that there's a Hopf bifurcation that if you are t is 2, there's a long time far away, so at time is 0, you have a convex problem and you steer towards the middle. At t is 1, it flattens off. At t is in half, you have to steer to one of these two goals. And so this is basically this is called delayed choice because naively you would think if you start at 0, you're going to go for one of the two goals, and you're going to decide immediately, because if you're slightly above 0, you're going to go to the +1. If you're slightly below 0, you go to the -1. This result says that that's not the way to do it. You actually have to wait. You steer towards the middle, you stay between the two goals, and you do that for a while, but not too long. You do that because you have what you can think of. You have a forward cone of noise. This is the width of this is. So if I want to go to you or to that chair, and my cone of noise is here, is like this, then I can steer in the middle because I will reach one of you. If I now go forward, then at some point my cone will no longer include these two goals, and I have to make a choice, right? And that means that the more noise there is, the wider this cone, the later I will make that decision. Conversely, the smaller the noise, in the deterministic case, I should make the decision as early as possible. So noisy means late. So, and it rings very well with the academic environment, where we're constantly have all these kind of deadlines that we have to meet, and it's all noisy, and we always have this tendency to wait as late as possible with our decision. And I'm telling you, it's optimal to do it this way. It also rings very well with religion. So I mean, I'm from the north of Europe, and so you can relate these solutions to high noise is high temperature, and low noise is low temperature. So in the north of Europe we have the low temperature solution, and in the south of Europe we have the high temperature solution. So I come from a Protestant background, and my mother always told me, don't leave for tomorrow what you can do today. So that's the low temperature optimal solution. And in Spain, of course, they all say mañana, right? So this is waiting as long as possible. So it makes perfectly sense to do it this way. So it's all in Greek. Okay. Here I have a little example of this. Let me, if you have time, let me skip this one. Let me go to the next one. So here you see an example of this. Let me see. So this is about the 14-dimensional dynamical system.
This video presents the MPPI algorithm and
let me show you this
experimental
video.
results on the Auto Rally platform at the Georgia Tech Autonomous Racing Facility. In all clips, the robot operates fully autonomously using only onboard computation at speeds approaching 20 miles an hour. MPPI, which stands for Model Predicted Path Integral Control, is a stochastic optimal control method that relies on forward sampling trajectories. These trajectories allow the algorithm to evaluate many models. Shown in green, in real time.
So here you see. So what you see here is the operation of this path integral control in iterations with this rate of 60 times per second. In each of these iterations, 10,000 samples are sampled, and with those samples, the optimal control is being computed. is being executed on the machine, 14-dimensional vector, and then at a clock rate of 60 hertz. This is done.
So X is the position of the car.
X is the state of the car, which is all the wheels and the accelerator and anything, all the knobs on the car. And also dynamical variable position and where it is, tilt, all the dynamics involving the car. Right? So you build a model. So there's a part that is about the model building, and then the control happens in there. There's about 10 or 12 control variables. And then you are making observations. You are in a current state, and you want to predict the car's behavior over the next second or so, which is these beams. Also, this is this future trajectories, and you in that model you simulate that. You incur the cost being, where you get off the road and those kind of things. And then based on those samples, you compute the optimal control. And that is then executed. And that is repeating at 60 hertz. Yeah.
The cost is infinite because of the voltage.
Infinite basically. Yeah, so you need for this, you need a model of the plant, right? You need a model of the vehicle here, and you need, of course, a cost function also, and So this is a very, very high dimensional problem, and it's real time, and it's stochastic, and it's nonlinear, and I think there's no other control method that can do these kind of things. Okay. Go on. Where am I? Yeah. Okay. So the control problem we have now cast into a sampling problem. And this is not solving the problem because the sampling can also be very, very hard. And so, for instance, here you see the same problem with the end GOS, the problem that I was having here before, and I'm now sampling this space with different strategies. I'm using I'm sampling n trajectories. And I can either use the uncontrolled dynamics, which is on the left, which is control 0. I sample with control 0, and I get some statistics. I told you I can use whatever control, and they always give asymptotically the same result, but they will more or less efficient. So if I use control 0, I get the results on the left, and if I put some other intermediate control, halfway the optimal control, I compute the optimal control, I divide it by 2, so it's a suboptimal control, and I get this, and I do the optimal control, and I get this. So what I do, I get the trajectories from this particular stochastic dynamics with a particular control. I compute these control weights, and I compute this cost to go term, which was this path integral solution, which is just these weights becomes in this sum. So this becomes the proxy for the integral. It becomes a sampling over these trajectories. And what you see is that what I did here, so if what I compute is the control cost of this solution, so I get the cost, which is high here, 31.52, and I also compute what's called the effective sample size. The effective sample size is basically, so I'm computing samples, but these samples are weighted. Some have a large weight, some have a small weight. And the intuition is that the more equal the weights are, the more efficient the sampler is. If I get a very skewed distribution of weights with some very large numbers and a lot of small numbers, I have an inefficient sampler. And my effective, although I have n samples, my effective number of samples is much lower than that number, right? And I can quantify this by something like this. I look at the variance of these weights, and this is something that gives me a number between 0 and n or 0 and 1 or something like that. So this is the effective sample size. And you see that if I use a suboptimal controller, I get a very low effective sample size. This is on the scale of 10. So 1%. So effectively you have 2 samples, which is these 2 basically. So here I have 3.5 samples, and here I have 9.5, which is almost 10 out of 10 samples if I sample with the optimal control. And so this is so one can prove a theorem that the better U in the sense of optimal control, so the lower control cost, the better controller, is also provides better samples in the sense of better effective sample size. That these go hand in hand. Right? Better control, better sample. And the optimal control, in the sense of control, it is the control that's optimal, that minimizes the control cost, requires only one sample. So this is what is called in statistics a zero variance estimator, right? And it's really curious because if we, so it means, so this S, if I remind you of this S of U, what it was, I can do this like this. Let me see. So if I look at this S of U, where is it? Here. So you look at this S of U. So it is a function of the whole trajectory. So this is the end state. This is some intermediate state. This is some noise. Here are some functions, etc. The statement is that this thing, of course, always gives a stochastic number, some random number back. But if and only if I replace this function U by the optimal control function, in that case, whatever tau, whatever trajectory I put in there, I always compute the same number. It's really, really crazy. And that's what happens here, right? And it's called, so that's why it's optimal. So if you only need one sample, it's clearly optimal because you only need one sample, so you're very fast done. And so this is, of course, but then you need the optimal control, and that's the whole thing we're after. I don't go in the proof. Well, one way to see that why this is happening is that if you look at slide 15 here, there's no, so here, here, you see that if the control is optimal, this reweighting term is absent. So there's no reweighting anymore, right? And that's why it's, so that's why you get what, well, it's maybe not the best explanation. You can, but I don't have time to do the proof here. Okay, so we want good important sampling to compute the good controls. So how we're going to do that? And the idea is what is called using something called cross entropy method, and it's called PICE, path integral cross entropy method. So the control objective that we have was, in terms of this KL divergence, it was this quadratic U squared term, which became this P log P term divided by P0, and there was this state dependent cost term here. And this we had to optimize, and you can write this whole thing actually as a KL divergence, this whole expression of this particular P of U hat and the optimal one. So you can write in terms of the optimal one, you plug in the optimal one here, and so and then there is this number which is just a number which doesn't depend on the control problem. So we see that if U hat is equal to the optimal control, this KL is 0, and we have minimized, we have find the best solution, right? So this is how we can write it. So this is one way to see the original control problem. Now it turns out that for the optimization, we decide to optimize the reverse KL. So we put a P star in front and a U star. So as you know, this measure is not symmetric, but for small, if they're close to each other, it's the lowest order, they are the same. But of course, in general, but okay, this is what's happening often in machine learning, that these things are interchanged if whatever is most convenient. And so if you then optimize this quantity, you can compute this quantity. So it is just P log P. So you get P star log P star, which is a constant, doesn't depend on U. So we get a P star log PU we get here. And then we estimate, we have to, so we estimate this by samples from that one. So this is how we estimate it. And this one we don't know, but we have an important sample for it. We do it with some other control U. So there's the control we're after, which is U hat, and we do that by sampling with a control U, which in principle is different, right? So we have two controls running around here. And so in this way, we can compute the gradient of this thing with respect to the parameters and optimize in such a way that you get to the optimal cost, optimal control. In a particular case, so to make it more concrete, so in the case that both this U, this sampling control, and the one that we want to compute are linear combinations of a fixed set of basis functions, say, so we have some parameters times some space-time dependent functions, and for both of them, then we can actually set the gradient equal to 0, and we get fixed point equations of this form. And these involves these are linear because of the controllers are linear, and we get basically we have to estimate some matrix here, and we have to estimate some vector here. This is the correlation of and this brackets involve sampling with respect to the optimal control, which we do with importance sampling. So we have a controller that estimates us these quantities, and with these quantities we can then compute the new parameters in this way, where this is A and B, and then we have a new parameters. We have a new controller, and with the new controller we can sample these estimates again, and we can iterate that. So we're repeating every time the same computation, but we're doing it every time with a hopefully better controller, and this way bootstrapping from 0 to get the best possible controller. So this is the iteration scheme that you start at theta n, you have a certain controller, which is maybe is this one, and with those you estimate these quantities, which are an and bn, which you estimate from the trajectories, and with those quantities you then estimate the new control parameters, and then you iterate that. Right? Now there is actually a nice, so this requires a lot of data, but there's a very nice data parallelism that is happening here, where I just want to tell you. So so you can use this, for instance, so in general, if we don't have this simplified linear scheme, but you would have some sort of a deep neural network, you would require the gradient computation. So you, in each iteration, you generate data from your model with a particular controller that you have at hand at that point, which is your important sampling. And so you get your data, and with your data you do the gradient computation, and you get a change proposal for the change of the parameters, and that which you can update your parameters and then iterate this. And the point is that this can be very nicely parallelized, because the data generation is just independent runs. So you can have just 10 machines all doing their own, generating their own runs. And then you have 10 machines with their data, and the subset of data on machine 1 can be used for the gradient computation, as in the sense of a mini batch, because this is also, this gradient computation is linear in the data. So you have a contribution from dataset 1, contribution from dataset 2, etc. So you can have here a gradient computation for the particular data set, and here for that particular data set, and then you just add all these contributions, and then you iterate this. So you can do this massively parallel without having to swap data between machines. Okay. So in the end, let me finalize this the end of this talk with just showing how this works on the control of a noisy Lorentz attractor. So we have a 3D Lorentz system with X is 3 component. This is the Lorentz attractor. Then we add some control and we add some noise, and then we generate 6 observations, x1 to x6, which are 6 points along this trajectory where you want to be close to. So the cost function now is at this particular time at ti, at t1 you want to be close to x1, at t2 you want to be close to x2, etc. And then we have this quadratic control cost. Sorry for this slipping out this term here. And so then we can do this adaptive importance sampling scheme, and here you see the effective sample size. So it starts, so this is between 0 and 1. So 1 is that you're very efficient in your sampling. 0 is that you're very inefficient. And here are different runs. And here you here reach the 50%. And so using many machines and many iterations, you can get the effective sample size going up, meaning that the sampling is getting more efficient, and meaning that your control is getting better and better. And so at this point, the controller typically looks like this. So here, this is over time. This is so the controllers of the form of a linear control feedback controller. So AX plus B, and and A is of course a function of time. This is the feedback control part, and this is the open loop part, the state independent part. Here it shows the open loop part, B, for the three different components. Oh, I should mention the observations are only on the first component of X. So only, not the whole state is observed, only the first component is observed. So that's here. Yeah. And so you see here it's going towards these observations. You see that happening over time. This is this B component of the first component, but the other ones also do certain things. But what's interesting also is this part here. Here you see the feedback part. This is A, and the blue one is A1. And so this is A11. So this is the diagonal term of A there. And you see that whenever there is an observation, this becomes very negative, basically meaning that it wants to stabilize around that point. If it is, you want to basically get to that point. If it is too high, it wants lower. If it's too low, it's higher. It's a feedback towards the point. But that only, it's like going to that target, and that only occurs for time up to that particular TI. Then you want to be there. Afterwards, you don't care anymore because there's no objective anymore. The system is free to go until it gets to a time where it has to be again close to another state, and then it kicks in the feedback control to make it large, because there's no need for feedback control and anywhere there in between. So this is just to illustrate that for such a chaotic system, you can compute these controllers, and that they are very nice and very non-trivial, non-obvious properties, and that you can compute them efficiently using this kind of an approach. And that's more or less the end of my talk. Let me summarize. So the path integral control is a class of control problems where the optimal control can be computed by sampling. It yields state-of-the-art results for channeling nonlinear, noisy, real-time control problems. It relates control theory to statistical physics, to the partition sum, and it plays phase transitions. The sampling efficiency can be improved by importance sampling, which takes the form of an adaptive controller. Optimal control and optimal sampling are related. Better controller are better samplers. Optimal controls are optimal samplers. Iterative and border sampling has a bootstrapping problem. Poor initial controller yields poor samples, leads to poor controller, so it's hard to get off the ground. And this I didn't. So this is something I didn't talk about, and I don't want to take more time. Is that you can also apply this idea to actually to time series analysis. So if you have some time series like the weather forecasting where you have latent state analysis, you have to do some latent state reconstruction, then these methods very much apply, and we have applied it, for instance, in the neuroscience context to estimating brain states from fMRI data. And that is the end of my talk, and here are some references, and thank you for your attention.
More questions or comments?
Thank you very much for the very nice talk. I have two questions. One is that I didn't understand very well what is the constant lambda that you have in your, for example, the change of measure, because you said that is something like the temperature, but for me that's like that should be like something like the size of fluctuations in the process, so like the diffusion constant or something like that. So are those things related, or?
Yes, it is. So it is basically. So here, so this lambda is R times nu. So it's basically, if you take R as 1, it's basically it's the noise, and nu is the noise covariance matrix. So it's the size of the noise, but it's also proportional. It is also, you can also appreciate, since the cost is so the cost term has this RU squared in it, right?
Sorry, can you remind me what was R?
R is this control cost here, this thing.
Okay.
So high noise is the same high noise is the same as having a large so you can make lambda large, high temperature, by either putting the noise large, yeah, loads of fluctuations, but also by taking R large, because taking R large, you only allow for very small controls, and in a sense it makes the system more convex. Take the other extreme, that if you have R is 0, you allow for wildly large controls, and you get a very, very difficult low temperature kind of a problem, right? So that's why that product matters.
Okay, thank you very much. And another one is related with the expression for P star, that it reminds me to the kind of expressions that you have in the context of large deviation theory with exponential tilting and all. So these frameworks are related in the asymptotic limit or something.
In fact, this asymptotic, this tilting is very similar to this cross entropy methods that they use there for efficient sampling. Is that what you refer to?
To the ensemble and all of these things.
It's the same. It's very similar.
Okay,
that's very similar.
Okay, because for them, I think that they have this problem that because what is nice here is that you have the generator for the process, so with the U, no?
Yeah.
So I think one problem that they have is that they can do the change of measure, but they don't know which is the generator producing this change of measure or something.
They don't know which U to use.
Which is the process that
They don't know which U to use. That's what you mean.
Exactly.
So this is this idea that you actually they know that if you use the optimal thing that you have a zero variance estimator, and you know that if you're optimal, but they don't know how to compute. And this is a proposal how to compute it in the time series case.
Cool. Thank you very much.
Comments or questions?
You have said that this path integral control is more efficient than others, than particle filtering and other things, but what is wrong with it? I mean, should have some drawbacks. Could you say what are the problems? Is computational efficiency? I don't know. What are the drawbacks of it?
Okay, so I already mentioned that if you know that the control has to enter in the same channel as the noise, right? So if I have for instance a two-dimensional system, and so dx1 is something with noise, dx2 is something with noise, and I add control to one of these things because I can control one, I cannot control the other. You're already outside of this framework. It doesn't work, right? So it's a very particular way that this noise acts. So that's one part of the answer. The other is that you're not controlling the noise. This is another thing. So there is nothing that makes this noise big or small. So if you take a financial problem, for instance, you can put your money in the stocks or you can put your money in the bank. And by that control, you're changing the noise. Because if you put it in the bank, the noise is zero, you get a fixed interest rate. If you put it in the stocks, there's a high fluctuation. So you're controlling the noise. Here you're not controlling the noise. Right? So that's another limitation. So there is definitely many limitations. It's not a panacea for everything, but for some things it works for some things. It's what it is.
Okay, thanks.
Just modify myself. But can you do the case without noise? So can you do the case without noise? Take no noise.
Yeah.
Zero noise.
Yeah.
In the Lorentz system, you have a chaotic system.
Yeah.
You can ask your say stabilize an orbit.
Yeah.
And there is no noise there.
Yeah.
Can you do that?
Well, so in the case, okay, this is good. Thanks. This is also a very good question. So in the case of zero noise, basically you can imagine that the sampling breaks down, right? So because in the zero noise, you get basically, oh, sorry, I forgot here to put these lambdas, but these lambdas are here. Mm-hmm. So in this case, so in the zero noise, lambda goes to zero. Yeah. So you basically have to extremize this function. Mm-hmm. So you get to a singular limit. So these path integral methods work well in the noisy case. The more noisy, the better. And because sampling gets easier in the higher noise case than in the low noise. So this is, yeah. But actually, so if you this question, so one of the things that you can do, so we have this iterative scheme. So you can think of a sort of an annealing procedure that you say, okay, I want to solve a deterministic control problem. I add noise to allow the path integral method to work. I solve it for finite noise levels. I get a decent controller that allows me to sample also for lower noise levels. And I lower the noise level, I do an annealing, and I get then finally to a deterministic solution. And that's actually an approach that I want to pursue in the quantum context. Okay, yeah.
Are there any more questions? If not, let's thank the speaker again. And just send me an email if you want to discuss something with it.
Good.
Lot of stuff. Language of freedom will be the same noise. Some additive components of the neuron, which are class of systems, you recommend them to be applied.
What?
We need to know the relation of the dynamical system. What if we have data? Can you?
Well, if you have data, you don't have a model.
Para mí, toda esta gente está luchando para sacar el óptimo y
Sí.
nosotros, o sea, yo lo que diría es que los puentes es un cambio de medida
Claro.
que sabes hacerlo.
Sí.
¿Sabes? Entonces lo suyo es cómo de bueno es el cambio de los puentes o cualquier un cambio de medida local.
¿O qué pasa cuando un chico quiere seguir esa vez? ¿No? Un poquito de
Claro, claro.
You can only control.
Bueno, pues lo hablas.
No.
If you don't have the plans, you cannot control.
Okay.
So if I give you a robot and there is some knobs on it and you don't know how the knobs, what the
Then
effect
you
of the
cannot-
knob is, you cannot control,
Okay,
right?
this is my guess.
I mean, this is all
Yes.
in a sense. If you don't know how the system works, you cannot control it.
No, but there would be more than knows exactly how the system is through a classification of different analysis to know, okay, this is the kind of analysis that I can control.
But the control people, they talk about system identification.
Yes.
So you have a system, you don't know the system, but you first have to identify the system.
Yeah.
That's basically writing the equation for that system. And once you identify it, then you can start.
Then you can see if it's a category and then.
Then you can have the hope to control it. But you first have to know what system you are dealing with.
Mhm.
Okay.
So I want to introduce Raul Terra
Nice to meet you.
Hello.
That was very interesting.
and
Raul, yes, correct.
We met before, I think.
Don't do that to me, please. Don't do that. Where was that?
I think in Granada, maybe it's in Granada seminar, maybe.
Could have been.
Yeah.
Montreal, maybe, or Granada itself.
Huh?
Montreal or Granada.
No,
Granada City, Granada.
Granada
Well,
seminar.
he's also from Granada, so.
Oh,
Yeah.
you're from Granada.
Well, I studied there, yeah.
Exactly.
So Joaquin Torres,
Fucking correct.
Yeah.
he was a postdoc with me many years ago.
Ah,
before he
didn't
became
know.
professor
Oh,
in
okay.
Granada.
Okay. Very
And,
nice.
so we have had some contacts and I know Jesus Cortes, I don't know where you are, Jesus Cortes.
I didn't know. He's not in the same
No,
department.
he's not there, he's now in Bilbao, but
Okay.
he was there in Granada. And I know also the Joaquin Marro, I remember him very well.
Yeah.
He introduced me to some good parties.
He did that. He was my thesis advisor.
Ah,
I know
okay,
him.
yeah.
I know him well.
I wouldn't ever put in the same phrase Marro and parties. Okay. No, I
But
did.
you
I don't know.
You don't know Marro.
I don't know well enough.
No, you know, that's the right conclusion.
One of the stories he always amazed me. I don't know whether he ever took you there. He took me once in Granada to a bar, which is run by a medical doctor who has a practice of medical doctor for like 3 days of the week on the coast. Now, on the coast.
Uh-huh.
And then the rest of the other 4 days, he loves opera. And he has this bar where he has a screen and he sings opera from behind.
Wow.
Okay.
I didn't know that.
I'll tell him. Never brought me there.
Jesus. No.
Yeah, I think that's a really life lesson. He likes the situation.
Okay, I might see him in a couple of weeks.
Oh, really?
Again, so
He's very old now, right?
he's retired many percent.
Yeah.
I think there's a thesis in Granada. I'm attending in a couple of weeks.
Okay.
So he might be. I'll ask him to take him to.
Yeah,
take him to
that's
this bar.
give him my greetings, my best greetings.
Yeah, well, well, okay, I have to leave now, so we cannot talk in detail.
Okay.
But we have been working on something in how to generate trajectories, joining paths with a low probability.
Okay.
So how to do
Ah,
that?
yeah.
When the
Oh,
So
like
might be-
a Schrödinger bridge kind of thing? or
bridges,
something?
Yeah,
no,
okay.
no,
stochastic
no,
bridges.
stochastic
Yeah,
bridges.
yeah,
So maybe there could be some contact points.
yeah,
and
definitely.
so maybe we should talk.
Yeah.
We tell you what we talk
Yeah,
here, and
good,
then
good,
from there on.
good. If it fits in my schedule.
Yes, when are you available? Tomorrow,
And-
for instance?
Well, that's what we're checking. We'll be best on Friday.
Okay.
because tomorrow could be, but I have not much time tomorrow. So tomorrow afternoon could be from 4 to 6, for instance.
For me, it's good.
Or Friday. So would you prefer? Tomorrow from 4 to 6 in the afternoon or Friday? Friday I'm free the whole day, so.
I'm fine.
He's.
For Friday, I have something at 11.
Friday morning, there was another meeting, I could try to move it. He has another meeting at 11,
Friday.
Friday.
Another meeting? I'm in the meeting?
No,
So
I'm
he
not
can
in-
not
okay.
join at 11.
I
So
can-
Friday not at 11, but Friday afternoon.
I cannot at
After
11.
Friday not at 11?
Yeah,
It's
yeah.
okay.
Yeah, it's,
Also.
it's very, yeah. I
So
have
I
another
think
meeting at 11, so
I
So
will
we
be
do
after-
Friday afternoon
Yeah.
after lunch, so Friday too, is that?
yeah.
A week from the morning.
Oh, but it's not good, okay, so then we do tomorrow.
No,
at
Friday,
12.
oh, yeah.
Or Monday, I don't know.
Oh, he's here on Monday?
Yeah.
Yes,
it's-
Oh,
it's
okay, Monday.
BMT Wednesday.
Okay.
Monday is
Monday
good
is
for
fine,
me.
except from 11 to 12.
Okay.
Except from 11 to 12,
Oh,
Monday is fine.
except,
So Monday after lunch?
At 12 or after?
Oh,
Yeah,
lunch?
12, 12.
Okay,
Both
Monday
good.
12.
Yeah, Monday 12.
Okay.
Monday
Cool.
12, typically people here have lunch at 1.
Yeah,
It's
so.
1 hour
Yeah,
enough.
okay, 1:30.
Yeah.
It's okay?
Let each other be scheduled another meeting.
Okay.
Okay,
Thank
have a
you.
nice week.
Monday,
Okay.
12.
12. Yeah. See you.
Okay, down. So I put-
Yeah.
Just a second, I'll send you the WhatsApp, if not, myself. So, there, I actually didn't tell you to give a gentle introduction, and you forgot. Because typically there are these things that they ask to have a very basic introduction, so everyone can.
So, yeah.
It's not definitely the case,
No.
but it's good because you got immediately the point about having discussion with people that are more expert in the.
Yeah, yeah, so I'm sorry about that.
No, it's just I was thinking, I forgot to request, and then I saw that it was actually asked for this. Because it was
Okay.
better for you, because then you're being big on the phone of technical stuff, and he's open the way better to discussions. I don't know if, let's see.
1:30 para 2:30.